Swayam Prabha. Digital India. Educated India.
Okay, we'll start. So we are on the 14th session. The topic is arches and plane frames. What is the difference between an arch and a plane frame member in terms of internal forces? What are the internal forces in a plane frame member? Shear force and bending moment are what you get in a beam. What's the additional thing you get in a plane frame? Axial force. Is it compression or tensile? It can be either of the two. What about an arch? Arch is a plane frame member actually, and typically the axial force is compression. Is it clear? Okay, so I think we looked at this in the last class. We talked of the principle of parity, and we said that if you apply the principle of parity, you can say that the deflection in this beam at the midspan when the left half is loaded will be equal to the deflection when the right half is loaded, because you're actually measuring the same deflection and viewed from two sides, right? Then if you invoke the principle of superposition, which says this plus this is equal to this, which you can do in linear analysis, then you can argue that the deflection here at the midspan will be half the deflection in the full beam. I brought this up because we asked a question in relation to arches. The question was this. Remember, we said that had this been fully loaded uniformly, this would have been a funicular arch, right? Now only one half is loaded, and it looks as though the arch is statically indeterminate. But you can invoke the same principles of parity and superposition and prove that it is actually statically determinate. The argument goes like this, same argument. Well, in this arch, the vertical reactions are statically determinate because 1/4 of this load will go here and 3/4 will go here. Whatever you do, regardless of what the horizontal reaction is. The question is, we don't know what this H is. And typically, most people would go and solve it as an indeterminate problem. There's no need to do that. The argument is, if you load on the right side, everything gets flipped over, but the H is going to be exactly the same, right? And if you add these two, then you will get this shape. And you know very well that if this is parabolic, and if the loading is uniformly distributed along the horizontal span, then this is a funicular shape. And what will be the horizontal reaction? This will be double, of course. If you call this H and you call this H, this will be 2H, 2H, right? What is 2H equal to? This load will also become 2W if you say 1/2 is loaded with W. Give me the answer. W Come on. Capital W. W, look. WL by 8H. That's right. That's right. Instead of W, you will say 2W. 2WL by 8H. That's all. So if we know this answer, then surely we know this answer. That will be half this. That's WL by 8H, which is Q0 L by 16H. Then you've got the complete answer. Now, what is going to be the difference between this behavior and this behavior? This is a non-funicular arch for this loading. So in which locations will the bending moment be 0? In this arch, in which location is the bending moment going to be 0? Huh? What do you mean left side? In this entire region it will be 0? Why? Because, okay, here where is the bending moment 0? Everywhere, because it's funicular. So we're saying this looks exactly like this, so this whole side should be free of moment and this side should be full of moment, is it? What logic is that? What is the bending moment at the crown? 0. Why? Why 0? So it's good, your intuition is good, but you have to always defend your intuitive understanding with a logical reasoning. Huh? How? Huh? No, let him answer. Calculating it become. Oh, you're saying if you actually do the calculation, that's a crude way. Without calculating, can you tell me it's 0? You're right, but that's not a brilliant answer. I want a brilliant answer.
If we load right side, then that point should be matched to the right side.
Okay, so I can have both having a non-zero moment, left side, right side.
Can't be 0 so both then have to be 0 0.
Yeah. No, that's right. So his answer is correct. Let's say it's not 0. That's how sometimes you prove. Then you have to decide, is it going to be sagging or hogging? Right? So let's say it is not 0. Then whatever moment I get here and whatever moment I get there must both add up to 0, because it's definitely 0 here. Now, the only way I can have a non-zero moment is if the moment here is sagging and here is hogging, or vice versa. Because plus minus will cancel. It will never happen like that. Visually you can see the curvature is the same. So either it has to be both sagging or both hogging. Which means if the moment here is M, this will be also M with the same sign. So the moment here must be 2M, and 2M is equal to 0, therefore M is equal to 0. That's how you should argue. But he did it the hard way. He said, look, I can multiply W by 4 with the span, and then I multiply H with this height, and I'm finding it's turning out to be 0. That's also a good point. So in this funicular arch, the bending moment and the shear force are going to be 0 at all points. But in this arch, the bending moment is going to be 0 here, here, and here, and elsewhere it's not going to be 0. Can you guess whether the bending moment in the arch is going to be sagging or hogging? How will you guess?
Sagging.
Which is going, the whole thing will be sagging moment, is it?
Under the load, surely sagging.
Under the load, surely sagging. Sure. Why? Because the load is there. No, but H is also there. How can you give me a clever way of figuring out whether it's going to be sagging or hogging?
Same takes as simply supported.
No, you tell me, give me the answer. Sagging or hogging in the left half, right half? Here it's going to be 0. Think like a designer, like an engineer. What is your ideal arch? Is your ideal arch a parabola for this loading? What will be the shape of the ideal arch? Huh?
Left side should be parabola, right side it's a straight.
Straight line. Then why don't you superimpose that arch on this arch and then tell me? That's how people did it. So if you do that, and we'll come to that, you will find that this is the free bending moment diagram. You're right, this part will be parabolic, this will be straight. Right? And if you superimpose here, if you had to keep the same crown location here, this should have been the arch you would have made. Yes or no? Yes or no? You should think like that. This is the funicular arch, this is the real arch. Real arch, looks wise, is symmetrical and it looks good. And the Romans made absolute semicircular arches. Alright. Now, looking at this, tell me which side will be sagging, which side will be hogging, and why? There's a theorem you may have studied. It's called Eddy's theorem. But don't remember any theorem. Use your brain for a change. Tell me. Left side should be sagging. Why?
Because horizontal force is almost half of the original.
No. Slowly. Tell me, for this arch and this arch, will the horizontal force be different? Will it be different or same? Will the horizontal force for the orange arch which we just added and the original arch for this loading for the same rise of arch H at the crown be different or same? Be different or same? You guys should go back to the Stone Age. Simple question. Different or same? Why do you think so much? Huh? Horizontal should be the same or will be the same? Why will it be the same?
Any point bending should be 0 and
No, for this, yes, at every point bending moment should be 0. So?
taking the simply supported beam and bending the moment contracting the edge.
See, it's very simple. Where do these two fellows meet? They meet at 3 points. This point, and this point. Right? So, the free bending moment you get here, this value, divided by h, is the same for both these or not? Because the bending moment is same for both. That's the argument. Now tell me, h is the same. And so? It's so simple. H is the same for this loading whether I put this arch or this arch, right? I should have given, the whole idea of giving a rise to the arch is to eliminate these moments to the extent possible, yes or no? These are sagging moments which get reduced by the hogging moment caused by H into Y, yes or no? How much y should you give to eliminate this moment? You must give this much y. Now, you did not give this much y. You gave only this much y. The y given is less. So, it will be sagging. Here in this part, you gave more h than what you needed. So, you're getting more hogging. And so, this is the basic formula that you use. And you can guess that in this region you'll have sagging, this region. Not because there is load on the left side, but because you're comparing the real arch with the ideal arch, the funicular arch.
The red color one is a zero bending moment diagram.
Yeah, this projected on the horizontal plane will look like that.
It is just,
Sorry?
it is obviously, it is below the zero bending moment diagram. So it is sagging and
Yeah, that's what we said. Not zero bending. Yeah, this is the ideal shape. You should have given that shape. If you give any shape other than shape, then that shape, then from the given shape by comparison you can predict with it. So we'll go through it in great detail. But now let's look at a 3-hinged arch. What is a 3-hinged arch? It is just rigid, statically determined, because you got a condition here. You got a bending moment there equal to 0, right? Let's say this point B and this is YB. Now, how to get the value H for this arch? Sorry? VA and VC. What is VA? Can you tell me? VA is P into, or VC is P into A by L. So vertical reactions are known. VA and VC are known. What is H? H is correct. Moment about. Moment about. This point is 0, this point is 0, this point also is 0. So moment about word you should never use. Moment at. Bending moment at. Bending moment at B is 0. So what is capital H? If the free bending moment at B is m naught B, what is capital H? Right. M naught B by YB. Yes or no? M naught B is in a simply supported beam. Whatever moment you get here, that divided by YB must be 0, because at that location this is equal to 0. Yes or no? This is not going to be 0 at any other location. You know this. So you should have given me the answer very quickly. Right? Let's say you know the rise at the crown of the arch. This is true. Agreed? Now, I can replace this as H into YB. Where can I replace this H into YB? Is this correct? Why is it correct? Sorry? M naught B is equal to HYB. Okay? But M at X is not M naught B. So I think this is a wrong way to write it. We'll just say this is correct. Now let's look at this. Let me make another arch keeping the same YB. If I keep the same YB and the loading is at the same location, I can say that since this is going to be equal to 0 everywhere, I can make a statement H is equal to M naught of X divided by Y FA. FA means funicular arch. This is a funicular arch. For this loading, this is the funicular arch because this shape imitates the bending moment diagram. Yes or no? So we can make this statement. Now, we can also say H is m naught b by yb. So we are making a powerful statement. For the same loading arrangement, if the ordinate at the crown or at any location B is the same in both these arches, then the horizontal thrust will be the same in both the arches. Can we say that? This equation is valid for this arch and for this arch. Yes or no? Both these arches will have the same H if they have the same YB. We can go one step further and say that m naught x can now be written as H YA fx, or in other words, the net moment. We should have ideally given this much of rise in the arch. Now, if you're giving some other rise, y of x different from yfa of x, you're going to get a moment. And the actual moment will be the same h into the difference in these heights, yfa minus yx. If yx is equal to yfax, then mx is going to be 0. Otherwise, it will be non-zero. That's a way to look at it. So, I should have given this arch. The moment I see a permanent load acting like this, I should have given this arch. But let's say the architect wanted this arch, okay, then I'll design for the bending moments that I get, and I can guess. Now tell me, in this region, is it sagging or hugging? In this region, you gave more y than you needed to, because you need to give only this much. So you look at this equation, this quantity was higher than this, so you get a negative moment, so you get a hugging moment here. In this region, sagging, and so on. You can use that concept. That's called Eddy's theorem. I'll come to that. But more interesting, if you had given a funicular arch, you would have got only an axial force in the arch, which is compressive. No bending moment, no shear force. So, if you compare the line of thrust, this is called the line of thrust, with the actual center line of your arch, and if there's any deviation between this perfect line of thrust in the ideal arch, then that deviation will give you bending moment, shear force, which was not there in the funicular arch. Are you getting it? At any location x. So, this will be of such magnitude that its horizontal component will be equal to h, and its vertical component will be the shear force in your equivalent beam. Agreed? But the line of action will be exactly tangential to the arch. But if you give a deviation, you will get a shear force and a normal force, and the resultant of these two will be equal to h, and you'll have a vertical shear force also. Now, the bending moment you get here will be non-zero and given by this quantity. We'll look more into this. So, we're going to end this topic on arches by saying, if it's non-funicular, what to do, how to analyze it. So, we'll come to Eddy's theorem. Eddy's theorem is basically this same equation which we proved, but the statement is like this: the bending moment at any section of an arch is proportional to the vertical intercept, the difference in elevation between the point of the center line of the given arch and the corresponding point vertically above or below on the corresponding funicular arch having the same horizontal thrust for a given system of loads. Okay? Clean definition. So, you guessed correctly, this part will be hogging, this part will be sagging, and this part will be hogging. Okay, this is how you can use Eddy's theorem to guess the distribution of bending moments. But mind you, supposing the horizontal thrust was not there, then the bending moments will be huge. At least those bending moments have been reduced to some extent because of the horizontal thrust and the rise in the arch. Got it? Okay, now how do you calculate axial and shear forces? Let's see. If you take any free body of the arch and you've already calculated the vertical reaction and the horizontal reaction, and you know some loading there, then you can find the vertical force here, which is like the shear force in your equivalent simply supported beam, and the same H is coming here. Now, this is one coordinate system and you have a bending moment there. This coordinate system with this slope theta x can be changed to a coordinate system where I resolve V and H in terms of N and S. N is the normal compression and S is the shear force. Are you getting it? Well, finally you have to design for this. You can't design for this. This is good in structural analysis but not very useful in structural design. In a beam, V is the shear force, but in an arch or in a frame with an inclined angle to the vertical, this is your shear force. Your shear force is not V, please note. Your shear force is S and your normal force is N, and you need to know both. If this is theta x, which is the same as dy by dx, tan theta is dy by dx, then you need to resolve them. You can easily do that. How do you resolve them? Write the equations. You can take theta and you will find theta holds triangularly the same relation to V and H as to y dash and 1. With this relationship, you can resolve N, take the components of both H and V, H cos theta plus V sin theta, and S will be minus H sin theta plus V cos theta. Okay? And you can write this elegantly in this matrix form. At any location x, if you have H and V and you have y dash, then by this transformation, this linear transformation, you can convert H and V to N and S. Mathematically, this is an elegant way to do it, and you can take x at discrete intervals as many points as you want and quickly do this transformation. Please note, had the arch been funicular, what would have been 0? S would have been 0. Your H and V would be such and your y dash would be such that shear force will be 0 and your bending moment also will be 0. Okay, we will see problems of that kind later. Now, next set of review questions you get after we finish every topic, we'll give you, please go through this. Some problems on trusses, pedestrian cable stayed bridge, cable with some interesting, with a pulley here, I think, frictionless pulley here. So try doing this. These are questions we give in exams and so on. And an interesting problem here. Okay, this is an arch with a tie here. Okay, so you can have some movement here. Try solving this problem. And there's another problem here. Please go through this. Do it leisurely. Here, no figure is given. You'll have to draw your own figure. Okay. So with that, we move on. This is a refresher course. So we don't do more than this. You go to the book and you can get more solved problems and you can practice more problems. We are now still here and we have to cover the next topic. We move, see how logically we moved. We started with support reactions. We didn't care what the structure was, but we are looking at primarily plane structures, planar structures. We looked first at beams. Then we understood how the beam concept could be extended to trusses. Then we saw how it could be extended to funicular systems, which are cables and arches. Now we go to non-funicular systems, which are frames, plane frames, and then we'll look at influence lines. In all this, you can assume rigid body behavior, but it will always help if you can imagine the deflected profile, because it's so useful and necessary in practice to know which part is sagging, which part is hogging, and that visually you should be able to get a feel. So we'll practice that. These are some topics we'll cover. If you remember, I showed you a real building will have frames in in two orthogonal directions, and for convenience we separate out frames in one plane and we analyze that plane. We assume, unless the building is subject to twisting, it's fair enough to assume that there's little interaction between the frames in the x direction with the frames in the y direction. And although we use words like column and beam, the correct technical word is beam column or plane frame element. The reason is all these elements are subjected to bending moment, shear force and axial force, right? Though you would and you are imagining that the column is subject to axial compression. No, there may be some loading situations where the column is subjected to axial tension. Can you give me an example? Yeah, but those are, you assume lateral loads, that's one loading condition, but you're ignoring gravity loads there, and then you might get uplift, but usually the gravity loads will compensate and still put in compression. So predominantly in the beam elements, we say that bending behavior is predominant. So we design them for bending moment and shear force, but there will be an axial force, and that axial force could be compression or tension. Similarly, the columns, predominantly we say axial compression, but under lateral loads and so on, in the ground floor and lower story columns, you will have high bending moment and also shear force. The shear force, that's why we talk of base shear, and you'll find this is one error many engineers make. They think column has to take mostly vertical loads. So you have very small sizes given to columns in flats. You can see here 230 mm by 230 mm. There's no way it can take the shear caused by earthquake loading. So you have to be sensitive to the fact that you need a certain plan area, cross-sectional area, which should be adequate to take the base shear and the bending moments. Okay. So let's begin with something very simple. Don't worry about stability, just look at this. Let's say I have a portal frame. This is, portal means gateway, okay, a rectangular portal frame. And let me give it supports like this, 2 roller supports, and let me try to push it horizontally like this, okay. It's a load. Can you draw the free bodies of this? This is now statically determinate, right? Quickly draw it. So we are now practicing left brain activities, which is drawing the bending moment diagram, shear force diagram, axial force diagram. Then we'll also practice drawing the deflected shape and comparing these two. That's the practice for today. So it's not difficult. You can take out this column, and this edge has to be balanced by another edge there, and there will be a moment there, and edge has to be reversed. So this is Newton's third law. So you travel from one end to the other end and you'll get this, right? Both these columns will be acting equal and opposite. Yes or no? So very easily we got, by drawing the free bodies of the 3 elements, the 2 vertical elements and the 1 horizontal element, at the junctions we know what's going on. There's no vertical reaction here, there's no bending moment here, this is what happens, right? Now you can draw the bending moment diagram. Look at this. Bending moment diagram, you take the beam on top, the horizontal element. You have a constant hogging moment, capital H into small h, so it will look like that. And you've got a bending moment 0 here and linearly varying like this. The fact that you have a straight line variation suggests that the shear force is constant. The shear force in this column is constant, it's capital H. Are you getting it? And we've drawn everything on the tension side. Now I have seen students draw this differently, and I want you to know that these are the mistakes we generally tend to make. Let's say a student draws it like this. Is this okay or is it wrong? Yes? Why is it wrong? Many people do such mistakes. Why? The beam, the rule is we draw the bending moment diagram on the tension side, right? Why? Well, you can draw on the compression side, but whatever you do, you must do consistently for both beam and column, for all elements, right? This picture is wrong. Why? The reason why in India we suggest you draw on the tension side is, if it's a reinforced concrete building, you know on which side, top or bottom, to put your steel, your main steel. This is hogging, so you need steel on top. That's why you draw the bending moment diagram on top. Now the point to note is, if you take this junction, this detail, you have a column and beam junction like that. Now, clearly you need steel on the top. That's because you have tension on the top. Now, that tension goes all the way here, here. It comes on this side. If you draw like this, you're suggesting the tension is on this side, that you can't flip. You see how consistent this is. If you're drawing this on this side, you have to necessarily draw it on this side. This is wrong. Because you got tension here, tension there, tension there, tension there, tension there, tension there, all the way, and it has, this point is common for both the vertical element and horizontal element. The same tension, you can't be tension here, you have actually compression here. So it should be automatic. When you draw something outward in one element, it should be outward in the other element. This is an important lesson to note, and don't make such mistakes. Okay? All right. We move on. Can you draw the shear force diagram and the axial force diagram? There's no need to worry about sign convention. You can draw on any side. Okay. Deflected shape. Shear force, okay, can you draw? Shear force will be constant here, no shear force here. Axial force will be compression here and no axial force here. You can draw those diagrams. But look at this bending moment diagram. You must learn to draw these diagrams. This is the deflection diagram. The deflection diagram is something that you use your right brain to draw. You notice that this is going to bend like this. Okay, it should be curved. It should be curved. It should be curved. This is nicely hogging, cleanly hogging, and this angle should be 90 degrees. Okay, these two should be curved. You feel that, right? Okay, so that's also called the elastic curve. And to complete the picture, this is your shear force diagram, this is your axial force diagram. You can mention that it's compression. Clear? From the free bodies you can do this. This is one example. We go to another example. Same problem. I just want to see you draw the bending moment diagram and the deflected shape. Bending moment diagram and deflected shape. Well, to play safe, always begin by drawing the free body diagrams, okay? So start here, P, you get P by 2 there, so you start with P by 2. What will you get here? You will get P by 2. Then you take this element, this same P by 2 will reverse as P by 2 there. Why? Why will it reverse as P by 2? If you join them together, there is no force which will show up, so that's one argument. Other argument is Newton's third law, every action has an equal and opposite reaction. So if this is downward, this will be upward P by 2, and then through equilibrium, so this is not equilibrium really, this is Newton's third law, and so this must be also P by 2, and then this P by 2 will reverse here, because when you join these two, nothing should be there. And that's it, and everything looks nicely symmetric, done. It shouldn't take you any time. And you notice there's no bending moment here, there's no bending moment here, there's only bending moment in this beam, and the moment is PL by 4. Okay. Now draw the deflected shape. We've done a similar problem in one of the first classes. So I'd like someone who didn't attend that class to attempt this. Did you come for the first class? So anyone, any latecomers here? What, you attended this course before? No? You want to draw? Come. Come. Just draw the deflected shape. That's all I want. The probable deflected shape on the board here. Take the black and the blue maybe, or green. You can show the roller supports if you want. And the columns remain vertical. Then you're violating that 90-degree angle here. We normally do this as though the answer will come like that. We'll be bold and draw nicely. You're sure this is going to be like this? Okay. Draw nicely. Okay. Then what about these guys? They should be straight in your opinion?
Yes.
Why is straight?
Because they won't take any bending.
No bending moment. Okay. So then, but compatibility, see, that's why your left brain is strong, right brain is not so strong. That 90-degree you're violating. So don't violate. It's a roller, it can roll, it's very good. That's it, that's all you have to do. So its column will spread its legs outward like that. Good. Yeah, very good. So that's right, that's how you should do it. There, he's drawn the same thing. Perfect. Got it? Then you can draw the shear force diagram for a beam, and axial force. Shear force will look like this and axial will look like this. Clear? So now there are 4 diagrams to draw in plane frames. Bending moment diagram is the most important diagram. Shear force and axial force are easy diagrams to draw. And then you have a deflected shape, which is a guessed shape. Need not be, you don't have the numbers. Here you have all the numbers, it's statically determined. It's based on guesswork, but you must reasonably guess whether there's bending or not, and if so, is it sagging or hogging, or where you're going to get tension on which side. Okay. Now try this problem. We'll do it together. A C-shaped frame is made by welding 3 identical bars AB, BC and CD. Each of length 4 meters to form rigid joints, right angles at B and C. The frame weighs 600 Newton. Draw a sketch of the frame suspended from a ceiling. So let's first see what the question is. You have a C-shaped frame, identical, so let's draw the C. This is C. And let's say A, B, C, D. The frame weighs 600 Newton, which means each Each of these legs is 200 newtons. Draw a sketch of the frame suspended from a ceiling through a hinged support connected at A. That means you take this frame, pick it up and hang it from the ceiling at A. Can you at least draw the shape? This is a JEE exam question. Draw the shape hung from the ceiling. Let me see how it looks. And then after you've drawn that's called the loading diagram, you have to analyze that frame. When you hang it there, it looks like it's unstable because you can play with it like a pendulum, right? Imagine there's no wind, nobody's playing with it, it's just hanging like that. It'll satisfy equilibrium. Can you analyze it, draw the bending moment diagram, deflected shape? It really tests your understanding. First of all, you must be able to visualize how to hang that frame. Normally you're given loading diagram. Here you have to draw your own loading diagram. How will you draw it? Can you try? Give it a shot. I drew it sitting on the ground. Now hang the fellow at A. Can you guess how it will be? Anyone? Want to try? Okay. Let me just show you because we are running out of time. Yeah? Center of gravity. Yeah, you want to try? You've done it. Okay. How to locate? Sure. Pass. No, but I want the values. More or less he did it. Okay, let's save time. This is what you do. Right? If you hang it from A, it will look like this. But how to get? Now, look at this angle. This, whatever angle this makes theta, because these are 90 degrees, will be theta here and here. So look at it carefully. This is 600 Newton. Now, let's find the center of gravity. The center of gravity is going to be bang in the middle here due to symmetry. But this, can you tell me how much this, if this is 4 meters, I think 4 meters is given to you. Each leg is 4 meters. Tell me how much is x bar, how much is this dimension? Quickly. It's going to be less than 2 meters, right? How much will it be? 2 by 3? No. How much is x bar? That means the distance between G and O. When you were in school, you would have got all this like that, but older we grow, the more we wear out. Yes? Shouldn't take you time. 1.333, 4 by 3, that's all. Okay, so you can work it out. 1.333. Okay, you know that, and it should look reasonably okay. Then you can get this angle if you like, and you know it's going to be in that plane, and you can work out. Now, I'll help you. You can calculate, and you'll find you don't need these angles. You'll find that you really could orient it, and this is 3.2 and 2.4. Let's say you got all this. With this you can work. I want you to at least now sketch the likely bending moment diagram and the deflected shape. This is how it's going to be hung. Even drawing this and finding these numbers is not easy, but let's say you've done that much. Once you find theta, you can find these. These are correct. Let's say you achieved this much. If you had a friendly examiner, he would have drawn this picture and given to you. But we are a little unfriendly here. We want you to derive it yourself. Now is the tough part. Can you draw the bending moment diagram of this frame? This is a rigid jointed frame. AB, BC, CD are welded at B and C. 90 degrees. Can you draw? And only self-weight. And the weight of each of these three parts is 200 Newton. So you have to really think. You can draw your free bodies also. Where will the bending moment be maximum? Can anyone guess? At one of those corners, right? At A, what's the bending moment? 0. At C, at D, what's the bending moment? 0. At C and B, which will be higher? B, the bending moment will be higher, right? How much will it be? Can you draw the probable bending moment diagram? You want to try? Just try. No harm. It's always good to start from the cantilever. You can't go wrong. So draw that, draw it on the right side. Finish it. It has to reach the end, no? You have to, what's that? How many curves it's taking? Okay, good. Pretty good. Well done. Not bad. Good. I am impressed. So let's take this free body, this fellow. Always start at the free end. The loading is 200 Newton distributed, no reactions here. So at C, you would get a vertical reaction which is 200 Newton and a moment there, 200 into 1.2. Why? Because this is 2.4. Got it? So DC free body is very easy. Then you take the other element. You draw CB. Okay, CB should have been drawn parallel to this. Anyway, at C, whatever you got here, you have to put ulta, right, to eliminate. So, if you got 200 up, you have to put 200 down. If you got 240 anti-clockwise, you have to put 240 clockwise. And the UDL is acting, the resultant load is 200 Newton. At this B, what's your vertical reaction? This 200 plus this 200, 400, and your moment will be this moment plus 200 into 3.2 plus 200 into 1.6. It all adds up to 1200 Newton meter, which is a massive moment at B. And then if you take the third free body, here you know the reaction at A, but we'll work it backward. Okay, whatever you got here at B, you have to put reverse here. So this 400 Newton, you have to put reverse. This was up, so this will be down. This was anti-clockwise 1200, this is clockwise 1200. Now you do a check. Sigma Fy equals 0, 400 plus 200 must add up to 600, which matches with your reaction. And do a check. Work out the moment at A, and you will find that it will be 0. That's your check. It should be 0. So that's all it takes. And this is the diagram. Okay, which he more or less got correctly. Maximum moment is here. That's it. Okay. The shapes you can roughly get, not very important. Then, this is not easy. Guess the deflected shape. If you can do all this, brilliant. Look at this. You are having tension on top. So it will be like that. You have tension on the inner side. You have tension on the inner side. Are you getting it? More or less a shape like this. And this B may not move much, but C is going to move a lot. All right. Good. We'll go, and you can draw your shear force and axial force diagram. Let's go to simple cantilever frames. We're just playing today with frames. Not difficult, getting the hang of it. Take a cantilever frame fixed here and free at D and C, and we are applying a load H. That's your loading diagram. Can you draw the free bodies and draw the bending moment diagram, shear force diagram, axial force diagram? Well, go to your support reaction. If you have load H acting there, horizontal reaction to the left H here, moment is capital H into small h, right? Right? Then draw your free body. There are 3 free bodies. You can separate them up and you can start anywhere. DB will be just hanging loose like that. No loads, no forces. BC is clean, pure axial tension of H. And only AB will be subject to, this H will get reversed here and it will have a horizontal shear H and a moment. You must be able to do all this very fast. Okay, now can you draw the bending moment diagram and the deflected shape? There will be no bending moment in the top region, DBC. And the bending moment here will be like a vertical cantilever. Tension on the left side or right side? Left side. That's your bending moment diagram. You should be able to do it like that in 1 second. And everything matches very well. Draw the deflected shape. It's like a tree in which it's being pulled horizontally. It will move like that, bending nicely, and the top entire region remains straight. Why? Because there's no bending moment. Later we'll learn how to calculate how much these deflections are, but at this stage we just draw intuitively the shape. Then you can draw your shear force and axial force we want to. Same frame, now we apply a moment. Can you do the same thing? Do it. We apply a moment at the free end. Your support reaction will be also equal to that moment, m0. Will you have shear forces? Yes. So if you find out m0, now take this BC alone. If you have m0, you don't get any shear forces. And dB remains like that, so here also no shear force. So don't assume you will have shear forces. Okay, got it? This is a classic case called pure bending. Bending is happening in ABC, dB remains straight. Draw the bending moment diagram. BC is hogging or sagging? BC, hogging. AB is hogging or sagging? So we can't say because it depends on which side you are standing, left or right. Okay, good. But once you decide how to draw the bending moment diagram here, you have no choice. So you draw a tension on this side. Look at this. Okay. Draw the deflected shape. It will look like that, similar to the earlier one, except that this part remains straight, this is curved, this is curved. Now, what is the shape of this curve? Let me ask you. What is the shape of this curve? You tell me, you didn't attend the earlier classes, so you're the right candidate. What is the shape of the curve? Supposing I say it's parabola, is it wrong or right? Huh? Someone said right. Who said right? Okay, prove it's parabola. If you integrate the moment, so moment is constant, so curvature must be constant, so if curvature is constant, then the rotation, the slope will be linear, and the derivative of that, the deflection will be second order, parabolics, right? So multiple choice questions. A straight, B parabolic, C segment of a circle, D none of the above. Most accurate answer you have to give. Now you change your mind. Why is segment of a circle most correct answer? Why is segment of a circle most correct answer? Pure bending. You can use, go back to the original Euler-Bernoulli theorem. M by I is equal to E by R. M is equal to EI by R. If M is constant and EI is constant, then 1 by R must be constant. That means R must be constant. That means it's part of a circle. Now, how can both answers be correct? He also proved it's a second order polynomial, and we also proved it's parabola. Which is, we also proved it is segment of circle. Which is more correct, and why is this error coming? Give me the correct answer to that, and then I'll say you have understood the subject. If you are a practicing analyst, you will say, "Kya farak padta hai? Both are almost the same," which is also true. Yeah.
Definition of curvature we assume due to that will not.
You are right, absolutely right. We made an assumption in your answer. We said that d squared y by dx squared is equal to curvature. That's an approximation. You know the actual derivative as denominator with. So yours is an assumed answer. This is an exact answer, 1 by r. Okay, but some marks we'll give for that also. All right. So we'll finish by some more cases. You have a load like this now. Okay, we'll go faster. Again, you draw free bodies, you find the reactions. If you have P here, you have P here, you have a moment P into A. Quickly draw the free bodies. You should be fast. Statically determinate structures, easily you should do it. And keep practicing until you master this subject. Then you can do statically indeterminate problem. But determinate, you must be an expert, and you must learn how to draw all the diagrams. Okay, so you've got this P is balanced by another P here. You can always start at the free end, right? Then you have a moment here, P into A anti-clockwise. dB is just sitting there, there are no forces there. Whatever you drew here, equal and opposite you have to draw here. So this P up, reverse P down, anti-clockwise PA, clockwise PA, and then everything balances. So you should just check whatever you drew here, does it match with the reactions you got here? Everything matches. Draw your bending moment diagram, it will look like that. No bending in this overhang part, no bending in the straight part, right? And try drawing your deflected shape, it will look like that. This part in the overhang will be straight and this part will also be straight. Okay, now you know the game. Last one. You have a UDL. Q. And you're given this length L by 2. So total load you know. Total load will be 3QL by 2, and you can work out the moment. The CG is acting here in the middle. You will get some moment. Again, draw the free bodies. Okay, now this dB is having some load. The total load here is QL. Total load here is QL by 2, and draw the reactions. QL squared by 2 here, QL by 2 here, QL squared by 8 here. Now be careful. We did the two overhang cantilever portions independently. Now when you join everything here, so you should not get any resultant force. When you join all these three elements at B, the resultant force at B should be 0. So work it out. QL and QL by 2 will get reversed with 3QL by 2, and QL squared by 2 minus QL squared by 8 is 3QL squared by 8. Direction also should match, and then you come here and balance these two. That's how you do it. You must be sure that you don't need someone else to check your answer. Why? You've got always an equilibrium check yourself. Draw this bending moment diagram. This will look like this. You have a high moment in this cantilever because of the larger span. You have a smaller moment in this, which is 1/4 of this moment. And these two moments are equal and opposite. Their difference, this minus this, spills over here, and drawn on the tension side remains constant. Okay? Deflected shape, everything bends. Everything bends. So you can get n number of questions like this, and I think there's still time to do this problem, okay? This looks like a funny beam, no? It's not a beam, it's a frame. It's a beam with a kink. It's a cantilever. You have to draw all possible diagrams. Now you don't ask what is the question. You say, I know everything. I'll draw everything under the sun. I'll draw the reactions. I'll draw the shear force diagram, axial force diagram, bending moment diagram, deflected shape. You can't have any question beyond that. Deflected shape is a little tricky, but let's do the others at least. Please give it a shot. Support reactions. That's the first thing you learn to do. Shear. 5 kilonewton, 5 kilonewton, 10 kilonewton, 10 kilonewton. Then the moment will be 10 into 3 minus 5 into 1 is 25 anti-clockwise. Got it? All of you got it? Now practicing engineers don't do any, they don't need to show anything to any examiner. They just do this one shot, and ideally they should not use calculator also. Got it? Support reaction, all of you got it with the directions correct? Okay. Now draw the three free bodies. The three free bodies. Where will you start? Always start at the free end of a cantilever. So CD. CD is not CD, it's very straightforward. Straight line. Do you understand the English I said? CD is not CD. Do you know the English? There's a word in English called CD, S-E-E-D-Y. You knew that? He's a CD fellow. Well, something like shady. Okay. So it's good to know your English also. Okay, good. So you've got this, and then you draw for BC. Go from C to B. Now look carefully. This you have to be a little careful. There's this. See, this 10 kilonewton you should not have put here. It's very important. Why? If you put here, you'll have to balance it with something there. Some people make a mistake. This 10 can be shared between this member and this member, but in this case it has to go fully to BC. Why? It's a cantilever. It can't, this part, this 10 will not be passed on to this member, right? So 10 will be here, 5 will be here. So when you join these two, you will get what you get in the original structure. You will get a 10. Are you getting it? Otherwise it will get cancelled over. These two have to be balanced. So 5 is balanced by 5, 10 is balanced by 10. And then you have a moment. This 5 into 1 meter is a couple which has to be balanced by 5 kilonewton meter. Are you getting it? That's it. Now you draw the last element, AB. And don't put these values, you derive them and make sure they match. That's how you check your answers. So you draw AB, whatever you got here, you copy upside down. 5, 5, 10, 10, and the moment also 5 kilonewton meter anti-clockwise 5. Now 10 has to be balanced by 10, 5 has to be balanced by 5, and see the moments. 10 into 3, 30 kilonewton meter, minus 5 is 25, and then compare this with this and you say, look, I got everything correct. That's how you do, that's how you check your results. Okay. Now draw all possible diagrams. Let's draw the axial force diagram. All three members have an axial force, and you will find it's all tensile because this 5 kilonewton is pulling and it's going to pull all the horizontal members horizontally. So 5 here, 5 there. The vertical is being pulled down by 10, so it's also got 10. But this 10 comes as a shear in the other member. So this is axial force. Draw the shear force diagram. There's no shear in CD, and this 5 becomes a shear force in this member, and this 10 becomes a shear force in AB. Got it? Now draw the bending moment diagram. Bending moment diagram looks like this. There's no bending moment in CD. Bending moment is all straight lines because there's no distributed loading and the shear force is constant. Bending moment is 0 at C, but it's 5 anti-clockwise tension on this side. You must draw it correctly, and whatever 5 you got there, it will be balanced by 5 here. And this is interesting. It goes to 25 hogging here, and so there is a point of contraflexure somewhere. You must draw this correctly. Now try drawing the deflected shape. In your deflected shape, CD will be straight, BC will bend such that you have tension on the left side, and AB will also bend interestingly such that you have hogging up to most of the region and a little bit of sagging. Well, you can draw it, but since I want you to understand what's going on. So you draw it yourself, but I want you to understand what is the effect of each of these two loads. If you apply only the horizontal load, can you feel it's going to bend like that? If you apply only the vertical load, can you feel it's going to bend like that? Now it's a competition between this and this, right? These two will add up and you can try drawing the net deflected shape. But this is intuitively you must get this feel. Okay, so this is just practice, and we'll continue in the next class with some problems. Okay, and move on to simply supported frames. With that we end. Thank you.